Okay, first we discuss chemical kinetics and quick revision. Okay, and okay. So we discuss chemical kinetics for quick revision, right? After that I will continue solid state chemistry, right? Chemical kinetics gives information about what? It gives information about rate and rate and factors affecting rate of reaction. Okay, so rate means what? If you have a reaction like this, A gives rise to B. If you have a reaction like this, A gives rise to B. Rate we can express in two ways. One is average rate, another one is instantaneous rate. Average rate. So average rate we can give like this one, minus delta A by delta T. With respect to reactant we will get minus sign as its concentration decreases with the time, and with respect to product we get plus sign as its concentration increases with the time. This is called average rate. It is called average rate if delta T value is high end. If delta T value is high, if you measure rate of reaction for long interval of time, that is average rate. If you measure rate of reaction for short interval of time, that is called as instantaneous rate. That is indicated by minus dA by dt or plus dB by dt. This is called instantaneous rate, where delta T value tends to 0. If delta T value tends to 0, average rate is called instantaneous rate. Okay, delta T tends to 0 means almost we calculate rate of reaction at a particular time. We calculate rate of reaction at a particular time. So we can represent graphically also like this. Concentration of A versus time. Concentration of A decreases with the time. If you calculate for long interval of time, okay, if you calculate long interval of time, minus delta A by delta T, that is called what? Average rate. Okay, if you calculate rate of reaction at a particular time, that means delta T tends to 0, almost the gap is 0, that means at a particular time. So if you measure the rate of reaction at a particular time, so for that we have to take tangent and we have to take slope. So negative of slope gives what? Okay, what is slope? And here A versus T, if you take dA by dt is a slope. Slope we get negative slope. Okay, negative slope we will get, so minus slope, negative of slope gives what? Instantaneous rate. If you take long gap, that is called average rate. Okay, if you take small gap, short gap, then that is said to be instantaneous rate. Similarly, with respect to product also we can calculate graphically. Okay. For example, if you take concentration of B, concentration of B increases with the time. Concentration of B increases with the time. If you measure for long interval of time, that is called average rate. If you measure for short interval of time, for example, small gap I am taking at a particular time, if you measure the rate of reaction, that is called what? Instantaneous rate. So this is what? Plus dB by dt. Directly slope gives rate of reaction. Here negative of, in this case negative of slope gives rate of reaction. Negative of dA by dt is nothing but what? Only slope. dA by dt is slope. So negative of slope gives instantaneous rate. Okay. If you go to reactions involving gases, and for the reactions involving gases, okay, rate may be given as, okay, change in pressure by change in time. Okay, change in pressure by change in time. With respect to reactants, decrease in pressure, okay, in a given time. With respect to products, increase in pressure within a given time. So change in pressure by change in time for the reactions involving gases. So what is the relation between rate with respect to pressure and rate with respect to concentration? So pressure term if you convert into concentration terms, we have PV is equal to nRT. So P may be written as N by V is concentration. So P may be written as CRT. Okay, so in the place of P, if you write, okay, CRT, then we get dP by dt is equal to RT is constant, so dC by dt. So this is the relation between rate with respect to pressure and rate with respect to concentration. And with the time, what happens to slope of this graph? With the time, slope increases or decreases? Decreases. You may observe here. At this time, this is the slope. At this time, this is the slope. And at this time, this is the slope. So with the time, what happens to slope? Decreases. That means with the time, whether rate of reaction increases or decreases? Decreases. With the time, rate of reaction decreases. Slope is nothing but what? That indicates rate. Slope indicates rate. So with the time, slope decreases, that means rate of reaction decreases. Okay, right. This is the relation between rate with respect to pressure and with respect to concentration. Next one, what is the unit for rate? Okay, M, change in concentration, that is M time inverse. Okay, or moles per liter per time, or liter we can write in terms of decimeter cubes. So moles per decimeter cube per time. Mole decimeter power minus 3 time inverse. If you take reactions involving gases, what we get? Change in pressure by time taken for that change. That means pressure units time inverse we will get. Pressure units time inverse. Atmospheres or torr, okay, millimeters you will get. These are the various units for rate of a reaction. Okay, if you have a reaction like this, AA plus BB gives rise to CC plus DD. Okay, for this rate can be expressed in how many ways? Rate we can express in 4 ways with respect to A, B, C and D. So rate may be given as, how we have to write, how to give relation between all those 4. We have to write stoichiometric coefficients in the denominator, that is 1 by A minus dA by dt, that is 1 by B minus dB by dt. Next 1 by C plus dC by dt and 1 by D plus dd by dt. Okay, so that is the rate. So that is equal to what? Rate is equal to what? Rate constant into concentrations of reactants. Okay, that is concentration of A into B. Okay, concentration of A into B. The powers are x comma y, for example. So these powers we can get theoretically or experimentally? Experimentally only. These powers x comma y may or may not equal to A comma B. The powers may or may not equal to stoichiometric coefficients A comma B. Okay, rate can be given like this. In 4 ways we can express the rate of reaction. Okay, rate is equal to what? Rate constant into concentrations of reactants. These powers we can get experimentally only. X comma y values we can get experimentally only. Those x comma y may or may not equal to stoichiometric coefficients A comma B. What about for simple reactions? What we get? And simple reactions, single step reactions or elementary reactions, what we get? The powers are equal to stoichiometric coefficients. The powers are equal to stoichiometric coefficients. Next, K is called here what? Rate constant or specific rate. Rate constant, or it is called specific rate. Since if concentrations of all the reactants is unity or 1 molar, the concentrations of all the reactants is unity, then rate becomes equal to rate constant. That's why that is called specific rate. Okay, if you take concentrations of all the reactants, okay, 1 molar, then rate becomes equal to rate constant. Okay, K depends on what? K depends on what? Temperature, catalyst, right, and nature of reactant. Whether is it depends on concentration or independent of concentration? independent of concentration for a given reaction. For a given reaction, if you measure K value at different intervals of time, whether changes or K value doesn't change. Doesn't change. At 5 minutes we are calculating K. At 10 minutes we are calculating T for a given reaction. Okay. After 1 hour we are calculating K. Is there any change in the K value or K value remains constant? K value remains constant. So K value at time T1 is equal to K value at time T2 for a given reaction at a given time. For a given reaction at a given temperature, sorry. For a given reaction at a given temperature. Okay then. Next one, the sum of these powers are called what? This is called what? Rate equation. Okay, rate is equal to rate constant into a power x into b power y. This is called as what? Rate equation or rate law or rate expression. This is called rate equation or rate law or rate expression. The sum of the powers x plus y, the sum of the powers involved in the rate equation is called what? Order of a reaction. The sum of the powers involved in the rate equation is called order of a reaction. So order can be obtained theoretically or experimentally? Experimentally only. X is called what? Order with respect to A. Y is called order with respect to B. Okay. What are the possible values for order and order? We may get 0, negative and fractions also. We may get order 0, negative, fractions also. Okay. Okay. Next, if you take complex reaction, more than one step reaction. More than one step reaction is called complex reaction. For complex reactions, rate equation we give with respect to slow step, or that is also called as rate determining step. Okay. And for complex reactions, we can give order with respect to we can give order for overall reaction or each individual step only. Overall reaction. Okay, in the case of complex reactions, we can give order for overall reaction only. Order is meaningless for each individual step of a complex reaction. Order is meaningful only for overall complex reaction. So order is meaningful only for overall complex reaction. That is meaningless for each individual step. We can give overall rate equation by proceeding with respect to slow step or rate determining step only. Okay. Right, next one. What about the sum of the number of molecules participated in an elementary reaction? The sum of the number of molecules participated in an elementary reaction is called molecularity. So if it is an elementary reaction, single step reaction, okay, what about its molecularity? A plus B. If it is a single step reaction, then its molecularity is A plus B. So for single step reactions, elementary reactions, both molecularity and order are same. Molecularity and order are same. For single simple or elementary reactions, what about x comma y values? A comma B. So then what about order of a reaction? A plus B. So for elementary reactions, order and molecularity are same. Okay. Next, the general definition of molecularity is that is the number of molecules simultaneously undergo collision to bring some chemical change. The number of molecules that undergo simultaneously collision to bring some chemical change, that is called molecularity. Okay. Now, in the case of complex reactions, whether molecularity is meaningful for each individual step or for overall complex reaction. Each individual step, it is meaningful only for each individual step, it is meaningless for overall complex reaction. Since for example, if you take a reaction, complex reaction, 2A plus 3B gives rise to products. It is more than one step reaction. It is more than one step reaction. Whether all these 5 particles undergoing collision simultaneously, all these 5 are not undergoing simultaneous collision. All these 5 molecules are not undergoing simultaneous collision. So whether molecularity equal to 5 or not equal to 5? Not equal to 5. Okay, so we have to give molecularity to each individual step of a complex reaction. Okay. And molecularity, what are the possible values for molecularity? And can we get molecularity 0? No, we cannot get molecularity 0, negative and fractions. And we cannot get molecularity 0, negative and fractions. What molecularity generally we may get greater than 3 or we may not get greater than 3. And molecularity we may not get greater than 3 generally, since the probability for simultaneous collision of more than 3 molecules is small. So generally molecularity cannot be greater than 3. Generally molecularity cannot be greater than 3, since the probability for simultaneous collision of more than 3 molecules is less. Okay. And what are pseudo order reactions? And pseudo order reactions, expected order is different from actual order. Expected order is different from actual order, or expected rate equation is different from actual rate equation. Such reactions are called pseudo order reactions. What are the examples? And acid catalyzed hydrolysis of methyl acetate, where the rate depends on water or independent of water. And independent of water, since we take excess amount of water. So acid catalyzed hydrolysis of methyl acetate is an example for which order reaction? Pseudo first order reaction. Inversion of sucrose also same. That is also an example for pseudo first order reaction. Okay. These are some basic concepts from chemical kinetics we have. Next one, collision theory. And collision theory. Okay. According to collision theory, okay, it explains when a reaction occurs, why rates of different reactions are different. This theory mainly concentrated on reactions involving what? Gases. Okay. First, gas molecules are assumed as what? Hard spheres. Gas molecules are assumed as hard spheres. That's why this is also called as simple collision theory or hard sphere collision theory. Simple collision theory or hard sphere collision theory. According to collision theory, for a reaction to take place, they have to satisfy, the reactant molecules have to satisfy 3 conditions. The first condition is they have to approach each other, they have to participate in the collision. That is the first condition. The second condition is at the time of collision they have to possess some minimum energy, that is called threshold energy. If energy is less than threshold energy, even though they participate in the collision, reaction cannot occur. Okay. The first condition is collisions. Okay. The second condition is they have to overcome some energy barrier, threshold energy barrier. Then only the reaction takes place. The third condition is they have to collide in proper direction. They have to collide in proper direction. But simple collision theory doesn't consider orientation. Simple collision theory doesn't consider orientation. Simple collision theory considered first 2 conditions. One is they have to participate in the collision. Second one is they have to overcome energy barrier. Okay, so to convert reactants to products, there exists an energy barrier, and this is called what? Threshold energy. Okay. Okay, first condition we'll discuss first of all. Okay, the number of collisions that occur per unit time per unit volume, that is called what? The number of collisions that occur per unit time per unit volume, that is called collision frequency. Okay, the number of collisions that occur per unit time per unit volume, that is called collision frequency. If you take 2 alike molecules, 2 different molecules A and B, if you take 2 different molecules A and B, how to calculate collision frequency? Na Nb d square 8 pi kt by mu whole power 1 by 2. Na Nb d square 8 pi kt by mu whole power 1 by 2. Na and B are the number of molecules of A and B per unit volume. D is average collision diameter. Okay, at the time of collision, what is the distance between those 2 centers, center of the spheres, that is called average collision diameter, D or sigma, that may be given as Ra plus Rb, and radius of A plus radius of B. If you take diameters, dA plus dB by 2. If you take diameters, we will get like this, dA plus dB by 2. What is mu? Reduced mass. How to give reduced mass andi? MA MB by MA plus MB. Right? So by using this, how many collisions are occurring, okay, per unit time, per unit volume, we can calculate. And if you take two different molecules, if you take two same molecules, and okay, if the reaction between like molecules, if you consider A and A, then it is given as Na square by 2 d square 8 pi kt by mu whole power 1 by 2. Okay, this is the formula for collision frequency, number of collisions occurring per unit time, per unit volume. This is the first condition. And what is the second condition? At the time of collision, they have to possess some minimum energy. This minimum energy is called what? Threshold energy. This is called threshold energy. This is the average energy of reactants. This is the average energy of reactants. So what is the extra energy we have to supply? Okay, this is the extra energy we have to supply, that is called activation energy. So activation energy is nothing but what? Threshold energy minus average energy of reactants. Activation energy is nothing but what? Threshold energy minus average energy of reactants, right? So according to simple collision theory, rate given as, rate is proportional to what? Rate is proportional to what? Collision frequency, that is ZAB. If you take reaction between two different molecules, ZAB into, okay, e power minus Ea by RT. This e power minus Ea by RT is called energy factor or Arrhenius factor. So this indicates how many collisions are crossing this barrier. How many collisions are crossing this barrier, that is given by energy factor or Arrhenius factor. This indicates total number of collisions. In this total number of collisions, how many are crossing this energy barrier, that is given by e power minus Ea by RT. Okay. Now we know rate constant is a measure of rate of reaction. So whatever the rate constant values obtained, or rate values obtained based on simple collision theory, okay, whatever the rate constant or rate obtained based on simple collision theory, okay, more than experimental values or less than experimental values. It is observed that more than experimental values. Okay, more than experimental values means it indicates that there may be one more condition to be satisfied for the reaction to occur. Okay, simple collision theory considered these two conditions. They have to participate in collisions, they have to overcome energy barrier. Okay, so to overcome this, okay, according to simple collision theory, we are getting more than experimental value. So to overcome this, they introduced another factor in the above equation, that is rate is equal to what? P into ZAB into e power minus Ea by RT. So this P is called what? Steric factor. So orientation is not considered. This is called modified collision theory. This is called modified collision theory. That is called modified collision theory. Okay. So by taking into consideration of orientation of molecules also, okay, another factor is introduced, that is P. How to calculate this P? And P is equal to rate by ZAB into e power minus Ea by RT. So this is nothing but rate obtained experimentally by rate obtained based on collision theory. ZAB into e power minus Ea by RT is nothing but rate obtained based on collision theory. Rate obtained based on collision theory. So rate obtained experimentally by rate obtained based on collision theory, that is called P. Generally P value changes from 0.01 to 1. P value 0.01 means out of 100 collisions, only one collision is satisfying orientation condition. 1 by 100. 0.01 means 1 by 100. If P value is 0.01, 1 by 100, that means out of 100 collisions, how many collisions are satisfying orientation factor condition? Only one collision is satisfying orientation condition. Okay, Nandi. So according to simple collision theory, they considered as hard spheres. That means from any direction the reaction may occur. From any direction the reaction may occur, but According to modified collision theory, the reaction cannot occur from all the directions. Okay, they have to collide in proper orientation, then only reaction takes place. Another limitation in the simple collision theory is, simple collision theory doesn't consider what? Simple collision theory considered only translational motions. Rotational and vibrational motions are not considered by simple collision theory. This is collision theory. These are points you have to remember from collision theory. Mainly those equations. What is the final equation we got? And rate is equal to P into ZAB into e power minus A by RT. So P into ZAB we can write as what? NA NB d square 8 pi kt by mu whole power 1 by 2 e power minus A by RT. This, if you compare with the K, rate is equal to K into concentration of reactants into concentration of, rate is equal to concentration of A into concentration of B and K. Okay. So from that what we get? And K equation, PD square into 8 pi kt by mu whole power 1 by 2 e power minus A by RT. Okay, and if you compare that with K into concentration of A into concentration of B, this is the expression for K we will get. If you compare with this A into e power minus A by RT, what is A and Arrhenius constant? This is Arrhenius equation. So if you compare these two, what is the expression for Arrhenius constant we will get it? PD square 8 pi kt by mu whole power 1 by 2. So from this previously questions given, okay. So A is proportional to what? And d square into t by mu whole power 1 by 2. A is proportional to d square into t by mu whole power 1 by 2. This question given, and Arrhenius constant is proportional to average collision diameter power 2 temperature and reduced mass whole power 1 by 2. At a given temperature, if it is mentioned, d square by mu power 1 by 2 will get. At a given temperature, if it is given, d square by mu power 1 by 2. Okay, this is collision theory. And what about transition state theory, or it is also called as activated complex theory or absolute rate theory? Transition state theory or activated complex theory or absolute rate theory. According to that, what? Reactants are not directly converted to products. Reactants are not directly converted to products. Initially they form a high energy species that is called activated complex, further breaks to give products. So there exists an equilibrium between what? Reactants and activated complex. There exists high energy configuration. There exists a high energy configuration that is called what? Activated complex. Through this high energy configuration, reactants can be converted to products. Okay. Let us consider activation energy for forward reaction, EAF, activation energy for backward reaction, EAB, and this is what? Delta H, enthalpy of reaction. So enthalpy of reaction is given as what? Activation energy for forward reaction minus activation energy for backward reaction. Enthalpy change we can give as activation energy for forward reaction minus activation energy for backward reaction. For endothermic reaction, delta H we get positive. That means EAF is more compared to EAB. And for exothermic reaction, we will get delta H negative. That means EAB value is more compared to EAF. Okay. Activated complex. In activated complex, some bonds are in the process of breaking, some bonds are in the process of making or forming. Okay. Next one, Eyring equation. What is Eyring equation we have? If you consider the rate constant for this process as K, if you consider the rate constant for this process K and equilibrium constant K star, then what is the equation for K? And we get KBT by H, K star we will get. Okay, just you remember this equation. Previously this question also given it. The expression for rate constant is KBT by H, K star. So K is equal to KBT by H. K star equilibrium constant we can write as from thermodynamics. Equilibrium constant we can write as e power minus delta G naught star by RT. This is called Eyring equation. That is called Eyring equation that gives relation between kinetic parameters and thermodynamic parameters. Further, if you substitute in the place of delta G as delta H minus T delta S, so finally what we get? Ln K by T is equal to what we get? Ln K B by H, ln K B by H plus delta S naught star by R. ఒకసారి చూడండి ఇంతేనా, minus delta H naught star by R into 1 by T. Then ln K by T versus 1 by T. This is in the form of y is equal to C plus mx. So if you take a graph of ln K by T versus 1 by T, slope is equal to minus delta H naught star by R, and this is the intercept. So from slope we can calculate what? Standard enthalpy change. Okay, that is also called as enthalpy of activation. That is the change in enthalpy during formation of activated complex. Enthalpy of activation, this is standard entropy of activation. This is what? Standard Gibbs free energy of activation. Okay, and finally what is the relation between enthalpy of activation and activation energy? Delta H naught star is equal to EA plus delta N minus 1 into RT. This is the equation we have, which gives relation between enthalpy of activation and activation energy. If you take bimolecular reaction, delta N value minus 1. The bimolecule means A plus B, and 2 molecules we are taking. Okay, what about delta N value? 1 minus 2. Delta N value is 1 minus 2, so we get minus 1. So for bimolecular reaction it is delta H naught star is EA minus 2 RT, and for unimolecular reaction it is delta H naught star is EA minus RT. For unimolecular reaction 1 minus 1, 0. Delta N value is 0. So we get delta H naught star is EA minus RT. So these are some equations you have to remember from transition state theory. Reactants are not directly converted to products. Initially they form a high energy configuration that is called activated complex, in which some bonds are in the process of breaking, some bonds are in the process of making. So that is called hypothetical species, and by using this we can calculate enthalpy of reaction. And Eyring equation that gives relation between kinetic parameter, that is rate constant, and thermodynamic parameters delta G, delta H and delta S. And this is the relation between enthalpy of activation and activation energy for bimolecular and unimolecular reactions. Okay, this is collision and transition state theory. Next one, what about Arrhenius equation? Arrhenius equation gives relation between K and temperature, K versus T. Generally, as temperature increases, what happens to rate constant? Increases. As temperature increases, what happens to number of collisions? May increases. Number of effective collisions may increases. Okay. The collisions may cross the energy barrier. So number of effective collisions may increases. So rate constant also increases. For every 10 degree rise, okay, for every 10 degree rise, the rate constant may increases how many times? 2 to 3 times. That 2 to 3 times is called what? Temperature coefficient. What is the formula for temperature coefficient? K at T plus 10 degree by K at T degree. We are rising the temperature by 10 degree, then how many times rate of reaction changes? That is called temperature coefficient. Generally its value varies in between 2 to 3. If at T1 temperature, okay, temperature rate of reaction is R1, and at T2 temperature rate of reaction is R2, and the temperature coefficient is mu, then what is the relation between R2 and R1? R2 is equal to R1 into mu power delta T by 10. R2 is equal to R1 into mu power delta T by 10. For example, for a reaction mu is 2, and we are rising the temperature from 10 degree to 40 degree centigrade. Then what is the relation between R2 and R1? And R2 is equal to, we get 8 R1. Delta T value is 40 minus 10, 30 by 10. That is 3. Mu value is 2. 2 power 3, that is 8. So R2 is equal to 8 R1. Okay, with increase in temperature, number of effective collisions may increases, so rate of reaction increases. Generally, rate of reaction increases by 2 to 3 times for every 10-degree rise in temperature. That is called as temperature coefficient. If temperature coefficient is given and rise in temperature is given, how many times rate of reaction changes? That we can calculate by using this equation. What is the relation between K and T and based on Arrhenius equation? K is equal to A into e power minus EA by RT, where A is called Arrhenius constant or free exponential factor or frequency factor. Okay. So what is A and what is the importance of A? A is the maximum rate constant possible for a given reaction. That is the upper limit for rate constant. Since if you take temperature tends to infinity, what we get? And something power 1 by T is 0, something power 0, 1. So if you take temperature tends to infinity or activation energy tends to 0, in both the cases what we get? And K is equal to A. So at high temperatures, or if activation energy is 0, the rate obtained is what? Maximum rate. The rate constant obtained is maximum rate constant. So A is also referred as maximum rate constant possible for a given reaction. A is also referred as maximum rate constant possible for a given reaction. A is the upper limit for K and okay. What about the units of A? Units of A are similar to units of K. What is the unit for K and nth order rate constant unit is what? Nth order rate constant m power 1 minus n, m power 1 minus n time inverse. M means we can write moles per liter or moles per decimeter cube. Okay, so the units of A and K are same. For example, A value is given 10 m second inverse. What is the order of the reaction? M second inverse. 0 order. M second inverse is the unit for which rate constant and 0th order rate constant. So if A value is given like this, 10 m second inverse, what is the order of the reaction? 0 order reaction. Okay. Next, this we can write with respect to ln. Ln K is equal to, we have ln A minus A by R into 1 by T. Okay. From this, if you plot a graph between K and temperature, okay, right, as temperature increases, K increases. Which type of increase? And exponential increase we will get. Which type of increase? Exponential increase. Or if you plot a graph between K and 1 by T, which type of decrease? And exponential decrease. Okay, exponential increase, exponential decrease. And if you plot a graph between K and activation energy, if you take a graph between K and activation energy for a given reaction at a given temperature, as activation energy increases, what happens to the rate of reaction? Decreases exponentially. As activation energy increases, rate of reaction decreases exponentially. And this is in the form of y is equal to C plus mx. So if you plot a graph between ln K versus 1 by T, which type of graph we will get? We will get a straight line with a negative slope, where slope is equal to what? Minus EA by R. So from slope we can calculate activation energy. And integrated form, what is integrated form? Ln K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2. So from this, if K1, K2, T1, T2 data is known to us, we can calculate activation energy. This is Arrhenius equation. Okay. You remember this equation and linear relation. This is a non-linear relation we are getting in between K and T, exponential relation. Here we are getting linear relation. Next, integrated form. This is integrated form. Okay, if you have two reactions and okay, if you have two reactions, one is with activation energy of okay reaction A to B, reaction C to D, activation energy here 50 units, here activation energy is 100 units. Okay, in both the cases I am rising the temperature from 50 to 60 degrees centigrade. In both the cases I am rising the temperature from 50 to 60 degrees centigrade. Which reaction is more sensitive to temperature changes? First reaction or second reaction? Second reaction is more sensitive to temperature changes, where ln K2 by K1 value is maximum. First case or second case? Second case, ln K2 by K1 value is maximum in the second reaction. Since if activation energy is high, temperature limits are same in both the cases. This is same in both the cases. If activation energy is high, K2 by K1 value is also high. Okay, where the increase in rate of reaction is high, in the second case increase in rate of reaction is high if you rise the temperature from 50 to 60 degrees centigrade. Okay, if activation energy is 0, then K1 and K2 both are same. So rate constant is independent of temperature. If activation energy is 0, K is independent of temperature. Right, this is Arrhenius equation. Next one, we have reactions of various orders for zero order reaction. From zero order reaction, what we have to remember? What is different? What about rate and concentration? Rate depends on concentration or independent of concentration? Independent of concentration. Whether rate depends on time or independent of time? Independent of time. What about rate unit and rate constant unit? Both are same. Rate and rate constant units are same. What is the rate equation? And we have differential form. dx by dt is equal to k naught into concentration power 0. Concentration power 0, something power 0 is 1, no need to write. So this is what differential form. So rate unit and rate constant unit both are same. Such reactions are called zero order reactions. Rate is independent of concentration, rate is independent of time, units of rate and rate constant are same. Such reactions are zero order reactions. Examples: photochemical reactions, heterogeneous catalysis reactions, those are zero order reactions. Okay, what is integral form? K naught is equal to x by t, or x is equal to k naught into t, which is in the form of y is equal to mx. So if you plot a graph between x versus t, you will get a straight line. X indicates what? Reactant concentration or product concentration? X indicates product concentration. So product concentration increases linearly with time. This may be written like this, and x may be written as a minus of a minus x or not. Yes, a gets cancelled, minus into minus will get plus x. So from this, if you take the expression for reactant concentration versus t, a minus x is called what? Reactant concentration. So this is in the form of y is equal to mx plus c. So if you plot a graph between a minus x versus t, linear decrease, and reactant concentration decreases linearly, product concentration increases linearly with time. Next, what about the expression for half life, the time required to complete 50% of zero order reaction? That is a by 2k naught. T of is equal to a by 2k naught. That means T of is directly proportional to A. T of is directly proportional to A for zero order reactions. So if you plot a graph between T of versus A, we will get a straight line passing through origin. Slope is equal to what? 1 by 2k naught. If you plot a graph between rate versus concentration or time, what we will get? We will get a straight line parallel to x-axis. Rate is independent of concentration, rate is independent of time. Rate is independent of concentration, rate is independent of time. Next, these two important and product concentration versus time, reactant concentration versus time. Okay. These are some equations we have to remember from zero order reaction. First order reaction. Okay, before that, okay, K naught is equal to x by t we have, from that what we get, x1 by t1 is equal to x2 by t2, x1 by x2 is equal to t1 by t2, or x1 by t1 is equal to x2 by t2. Okay, within 1.5 off lives, how much percentage of reaction will be completed? 75% of the reaction completed. So to complete 75% of the reaction, how many off lives are required? 1.5 off lives. To complete 100% reaction, 2 off lives are required. So within 2 off lives, 100% reaction will be completed. Okay. Within 2 off lives, 100% reaction will be completed. Zero order reaction. Now first order reaction. What is differential form? Dx by dt is equal to k1 into a minus x power 1. Concentration of reactant at that time. The concentration of remaining reactant at that time, where we are taking the rate equation. So rate is proportional to concentration of reactant at that time. Right. What is the unit for K1? Time inverse. This is the differential form. What is the integral form? K1 is equal to 2.303 by t log a by a minus x. This is the integral form of rate equation. Which reactions are examples? And one special example we have for first order reactions. What is that example? Radioactive decay. Radioactive decay or radioactive disintegration follows first order kinetics. Radioactive decay follows first order kinetics. So from this we can get various equations. Ln a minus x is equal to minus k1t plus ln a, that we will get during derivation. Okay. Or log a by a minus x is equal to k1 by 2.303 into t. Okay. So this is in the form of y is equal to mx plus c, and this is in the form of y is equal to mx. We will get graphs. Okay. Here slope is equal to minus k1, here slope is equal to k1 by 2.303. And if you take the expression for a minus x, what is the expression for a minus x we will get from this? A into e power minus k1t, a into e power minus k1t. So if you plot a graph between a minus x versus time, which type of decrease? Exponential decrease. Okay, in the case of zero order reaction, initial concentration of reactant decreases linearly. In the case of first order reaction, concentration of reactant decreases exponentially. Okay, from this you can take for product concentration also. Product concentration, what we get? If you bring this x right side, x is equal to a common 1 minus e power minus k1t. Okay, if you plot a graph between x versus t, product concentration increases exponentially. For zero order reactions, reactant concentration decreases linearly. For first order reactions, decreases exponentially. For zero order reactions, product concentration increases linearly. For first order reactions, product concentration increases exponentially. Okay. Right. These are some equations you have to remember from first order reaction. Okay, and వీటిని rearrange చేస్తే ఇవి వచ్చేస్తాయి ఇవన్నీ equations. Okay. Next one, what is the expression for half life? 0.693 by T off. So therefore, whether half life depends on initial concentration or independent of initial concentration? Independent of initial concentration. T off is independent of initial concentration for first order reactions. Next, if you apply K1 at time t1 is equal to K1 at time T2, K1 at time T1 is equal to K1 at time T2, what we get? At time T1 we get 1 by T1 log A by A minus X, 1. At time T2 what we get? 1 by T2 log A by A minus X2. Okay. Based on this we got what is the concentration of remaining reactant after n half-lives? What is the concentration of remaining reactant after n half-lives? A by 2 power n, where n is the number of half-lives. N is the number of half-lives. Okay, after 2 half-lives, what is the remaining concentration of reactant? A by 2 power 2, A by 4. A by 4 means 25%. Remaining concentration, remaining percentage 25. Completed 75%. Okay, that table we discussed. T ops A minus X and X. 1 half-life A by 2, A by 2. 2 half-lives A by 4, 3 A by 4. 3 half-lives, remaining concentration based on this equation, A by 8. Remaining A by 8 means completed 7 A by 8 and so on. Remaining 50% completed 50%. Remaining 25% completed 75%. Remaining 12.5% completed 87.5% and so on. T off versus number of half-lives versus remaining concentration of reactant and product concentration for first order reactions will be like this. Number of half-lives, the time required to complete 99.9 kadandi, to complete 99.9%. How many half-lives? 10 half-lives. To complete 99.9%, 10 half-lives are required. To complete 99% of first order reaction, okay, how many 90%? Okay, what is the relation between time required to complete 99% and 90%? T 99% is 2 into 90%. If you take 99.9, we get 3 into T90. 99.99 if you take 4 into T90 we will get, and so on. Okay, if you see the difference, the time required to complete 75% of zero order reaction, how many half-lives are required? For zero order reaction, 1.5 half-lives are required, but for first order reaction, 2 half-lives are required to complete 75% of reaction. Okay. Next, we discussed radioactive decay. Radioactive decay follows first order kinetics. So whatever the equations we have for first order kinetics, all these equations are applicable to radioactive decay also. But in the case of radioactive decay, inverse of rate constant is called what? Average lifetime of radioactive substance. Inverse of rate constant is called average lifetime of radioactive substance. So the formula for average lifetime is 1 by K1, and 1 by K1 means what we get? 1 by K1, if you bring this to left side, T off by 0.693, that means we get 1.44 into T off. This is the relation between average lifetime and off lifetime. Average lifetime and off lifetime. After n average lifetimes, and if T is equal to n average lifetimes, what is the formula for remaining concentration of reactant? After n average lifetimes, what is the formula for remaining concentration of reactant? That is 1 by e power n into A. After 1 average lifetime, the concentration changes to 1 by e of its initial value. After 2 average lifetimes, 1 by e square of its initial value. After n average lifetimes, the concentration changes to 1 by e power n of its initial value. And how to calculate age of fossil fuels, okay, or age of sample woods, okay, by using this equation only. T is equal to what? 2.303 by T log A by A minus X. T is equal to 2.303 by K1 log A by A minus X. From this we can calculate age of dead animals or dead plants. Age of dead animals or dead plants. Such method is called as carbon dating method. So that is based on radioactive carbon, that is what? C14. C14 is a radioactive element that undergoes radioactive decay to give what? N714 plus beta particles. With the time, what happens to radioactivity? And it decreases. With the time, radioactivity decreases. Based on that, we can calculate age of dead animals and dead plants. Okay. So A, initial concentration. Initial concentration means activity of fresh sample, and activity of fresh sample by activity of dead sample or dead plant. Okay. Or we can calculate number of beta particles emitted in fresh sample by number of beta particles emitted in dead sample. Okay, right. These points you have to remember from first order kinetics. Okay. Next one, second order reactions. Second order reactions. What is differential form of rate equation? Rate is equal to rate constant into concentration of reactant power 2. This is the differential form of rate equation. Okay, what is the unit for K2? And m power 1 minus n, we have 1 minus 2, that is m power minus 1 time inverse. M may be written as moles per liter, moles per decimeter cube. Okay, Rp inverse, time inverse for the reactions involving gases. Okay. Now if you do the integration of this equation, we will get 1 by A minus x is equal to K2T plus 1 by A. So which is in the form of y is equal to mx plus c. So slope is equal to K2 and intercept is equal to 1 by A. And further simplification gives what? K2 is equal to 1 by T into x by A into A minus x. K2 is equal to 1 by T into x by A into A minus x. This is the integral form of second order rate equation. What is the expression for average lifetime? Sorry, half lifetime. The time required to complete 50% of the reaction, that is 1 by K2A. That means T of is inversely proportional to initial concentration. T of is inversely proportional to initial concentration for zero order reactions. This is the differential form. If you do the integration, we will get this equation, and further simplification gives this equation. And if you apply half-life conditions, what are half-life conditions? After half-life, remaining concentration is A by 2, product concentration is also A by 2. Those we have to substitute. X is A by 2, A minus X also A by 2. A by 2, A by 2 gets cancelled. So we get T of is equal to 1 by K2A. Inverse relation we have. Okay, now if you apply that one, K2 at time T1 is equal to K2 at time T2. K is independent of what? Time for a given reaction. You may calculate at any time, rate constant we get same. Okay. K2 at time T1 and K2 at time T2, if you apply, what we get from this equation? 1 by T1 into x1 by A minus x1, that is equal to 1 by T2 x2 by A minus x2. Okay, so from this, at one time the percentage of reaction completed is known to us. At another time, what is the percentage of reaction completed, that we can calculate. Out of these four, 3 are known to us, the fourth one we can calculate. What is the expression for A minus x and after n half lives? If n is the number of half lives. For first order it is what? A by 2 power n. A minus x is equal to what? A by 2 power n. For second order what we get? A by n plus 1. A minus x is equal to A by n plus 1. So if you see the relation between number of half lives, A minus x and x. If you take one half life, if you say substitute in the place of n as 1, what we get? A by 2, remaining completed also A by 2. If you substitute 2, A by 3, 2A by 3. If you substitute 3, A by 4, A by 3 plus 1, 4, completed is 3A by 4. that is 50%, 50%. This is 33.33%, 66.66%. 100 by 3, here 25, completed 75. So to complete 75% of zero order reaction, how many half lives? 1.5 for zero order. For first order, 2 half lives. For second order, it is 3 half lives are required. Okay. So mainly you remember this graph and 1 by a minus x versus t. Another one we can get t of versus 1 by a also, which is in the form of y is equal to mx. T of versus 1 by a, we will get a straight line passing through origin. And last third order reactions. What is differential form? Rate is equal to K3 into a minus x whole power 3. That is differential form. If you do integration, we get 1 by a minus x whole square is equal to 2k3t plus 1 by a square. 1 by a minus x whole square is equal to 2k3t plus 1 by a square. 2 we will get it. Okay. K3 equation, rate constant, 1 by 2t into x into 2a minus x by a square into a minus x whole square. And lastly, the expression for t of 3 by 2k3 a square. This is in the form of y is equal to mx plus c. 1 by a minus x whole square versus time gives straight line. If you are getting straight line, that is said to be third order reaction. That is called graphical method. What is graphical method? If you get 1 by a minus x versus time straight line, that is called second order reaction. If you get a straight line by taking a plot of 1 by a minus x whole square versus time, that is called third order reaction. Such method is called graphical method. Okay, only these equations are enough and relatively not important compared to other order reactions, third order reactions. Just you remember these 4 equations. Differential form again you will get directly. Integral form you remember easily like this. Here we get power 2, here 2, here 2. Okay. So for nth order reaction, what we get? Rate is equal to Kn into C power n, concentration power n, or a minus x power n. Rate is equal to Kn into a minus x power n or C power n. Next, this equation, relation between a minus x and t. 1 by a minus x whole power n minus 1 is equal to n minus 1 into knt plus 1 by a power n minus 1. That is the equation between, that is the relation between a minus x versus t. And what is the expression for half life? T of is proportional to 1 by a power n minus 1. T of is proportional to 1 by a power n minus 1 for nth order reaction. So for nth order reaction in general, if you take a graph of (1 by a minus x whole power n minus 1 versus t), we will get slope n minus 1 into k, intercept 1 by a power n minus 1. But this is not applicable to first order reactions. That is not applicable to first order reactions. Okay, here we are getting rate is directly proportional to what? C power n. We are getting rate is directly proportional to C power n. If you apply rate at 2 different concentrations, we can calculate what? Order of a reaction. So if you take R1, R2, rate of reaction at 2 different concentrations, C1 and C2, and if you simplify, finally what we get? N is equal to log R2 by R1 by log C2 by C1. So by using this we can calculate order of a reaction. That method is called as, what is the name of that method? Andi? Differential method. Okay, Van 't Hoff differential method. Generally we follow which rates? Andi? Initial rates we follow. Okay, after mixing the reactants immediately we can calculate rate of reaction. Since no reverse reaction, no formation of products, so no disturbance from products, so generally we follow initial rates. Okay, so if concentration I am increasing from 1m to 2m and rate is increased from, okay, rate is increased from 2 units to 4 units, for example, rate is increased from 2 units to 4 units, what is the order of the reaction? Concentration we are increasing by how many times? 1 time. Rate is also increased by 2 times, sorry, concentration 2 times, rate is also increased by 2 power 1 times. So what is the order? 1 will get. So the power is nothing but order of the reaction. So simply you can verify like this, simply you can verify like this, otherwise you may substitute in this equation, will get 1 only. Log 4 by 2 log 4 by 2 means log 2, log 2 by log 2 by 1, log 2, log 2, log 2 gets cancelled, we get order 1 only. Okay. This is called a differential method. Since we are using differential form of rate equation, we are using differential form of rate equation, so that is called differential method. Next, off-life method. From that, T off is equal to what we have? T off is proportional to a power n minus 1. So if you apply this equation at 2 different initial concentrations, let us consider T1, T2 are half-lives at A1 and A2 concentrations. T1, T2 are half-lives at A1 and A2 concentrations. Then what is the expression for order of a reaction? 1 plus log T2 na A2 na? T1 by T2 by A2 by A1. Antena చూడండి ఒకసారి. అంతేనా? And is equal to 1 plus log T1 by T2 by log A2 by A1. Okay, for example, T off versus A data is given like this. A 1m, A is changing from 1m to Tm, half-life is changing from 100 seconds to 50 seconds. Half-life is changing from 100 seconds to 50 seconds. What is the order of the reaction? Here we are increasing the initial concentration by 2 times. Half-life is decreasing by 2 times. T off is inversely proportional to A. That means what is the order of the reaction? Second order. T off is inversely proportional to A. So that is second order reaction. Otherwise we can calculate by using this equation. 1 plus log T1 by T2, 50 by 100 by log A2 by A1, that is 2 by 1. 51s are 52s are. 100 by 2 kada? T1 by T2, right. T1 by T2, that is 50 by, sorry, 100 by 50. 2 times gets cancelled. Log 2 we are getting gets cancelled. So 1 plus 1, what we are getting? 2. Order of the reaction we are getting 2. So this is called Van 't Hoff differential method. This is called what? Half-life method. This is the half-life method to calculate order of a reaction. If you have a reaction like this and A plus B gives rise to product, if you take B excess, then rate is proportional to concentration of A only. Okay, such method is called what? Oswald isolation method. Such method is called Oswald isolation method. Individual orders we can determine based on Oswald isolation method. If you take A excess, then rate depends on B only. We get order with respect to B. If you take B excess, we get order with respect to A. Okay. Another type of question, if A minus X versus time data is given. If A minus X versus time data is given, how to verify it? If time, for example, 0, okay, 1 second, 2 second, like that. A minus X, remaining concentration of reactant 100 m, for example initial concentration 100 m, next 50 m, 25 m. What is the order of the reaction? Within 1 second how much decreased? 50. In the next 1 second also 50 decreased. If same amount decreases, what about order of the reaction? If same amount decreases, order of the reaction is 0. If same percentage decreases, first order. If same percentage decreases, that is first order. Antena? This is wrong ration kada? Right, sorry. 50% kada ikkada? Right, sorry, first order. Here the concentration decreased by 50%, here also the concentration decreased by 50%. So order is 1. If it is 0 order, what about the change? 0, 1 second, 2 second, A minus X. If you start with 100 m, if it is changed to 50 m, what about here? If it is 0 order, 0. Here it is decreased by 50, here also it decreased by 50. Then order of this reaction is 0. If same amount decreases, 0 order. If same percentage decreases, first order. Okay. If these two are not correct, then you may go to second order, right? Otherwise, we have to verify whether it is second order or not, like this only. K2 is equal to 1 by T2 minus T1 into 1 by A minus X1 minus 1 by A minus X2. This data we have to apply at different intervals of time. The data we have to apply, the data we have to substitute at different intervals of time, which gives same K2, that is called second order reaction. Okay, for example, I am giving data like this. 0, 1 second, 2 seconds, for example, A minus X, what about order of this reaction? Okay, A minus X versus time, I am giving like that. What is the order of the reaction? Second order. Okay, what is half life and here? 1 second. Within 1 second, 50% of the reaction is completed. Okay, 25 remained means how much completed? 75%. To complete 75%, how many half lives are required? 3 half lives are required. So that is second order reaction. Otherwise, we have to verify by using this equation. Okay, for example, if it is 0 order, what we have to get? 0 order if it is. Okay, A minus X, 100, 50, 0. Within 2 seconds the reaction will be completed if it is 0 order. If it is first order, what we get? Okay, already the same example we discussed, I think. 100, 50, we have to get what? 25. After 2 seconds, 25. After 3 seconds, we have to get 12.5. Here minus 50%, here minus 50%, here also minus 50%. Here what? Minus 50, same amount, minus 50. Here same percentage and first order. After 3 seconds, we get 12.5 only after for a first order reaction. Okay. So this is a second order reaction. Otherwise, we can verify by using this equation. You may verify by using this equation also. And K2 is equal to 1 by T into X by A into A minus X. This also you can follow. Okay. మీరు మళ్ళీ ఇది స్పెషల్గా గుర్తుపెట్టుకోవాల్సిన అవసరం లేదు. No need to remember this equation specially. This also we can follow. But while you are applying this equation, you have to substitute like this. For example, we are applying for this data and this set of data. What is time? 1 minus 0. 1 we have to write. Here we are writing T2 minus T1. Okay. Here time, how we have to write it? Time taken for this change. What is the time taken for this change? 1 minus 0 into X. How much converted to product? 100. Okay, initial concentration is 100, remaining 50 means how much converted to product? 50. What about initial concentration? 100. What about remaining concentration? 50. So what we are getting K2 value? 100. K2 value at 1 second. We calculated K2 value at 1 second. Now if you calculate K2 value at 3 seconds, 1 by, if you take this data, 3 seconds minus 1 second, 2 seconds, into x and what is x value? 50 converted to 25 means how much converted to product? 25. What is initial concentration? 50. Here initial concentration 50. What is remaining concentration? 25. What we got? 1 by 100. We got same K2. So it is a second order reaction. You can substitute in this equation or in this equation. Okay. This type of questions important, right? So this is about reactions of various orders. Next we have to discuss what steady state approximation, complex reactions, Lindemann's theory of unimolecular reactions. Okay. Over. Next one, steady state approximation or steady state principle. Mainly JL students, they have to study up to this, and after that Lindemann's theory of unimolecular reactions. Steady state approximation actually not mentioned in your syllabus, but while we are studying Lindemann's theory, steady state approximation is required. Okay, and complex reactions also not mentioned in your syllabus, but briefly once you revise complex reactions. Okay, right. Steady state approximation. If you have a reaction like this, and A gives rise to B gives rise to C, or I gives rise to C, where I is unstable intermediate. If I is unstable intermediate, according to steady state approximation, the change in the concentration of intermediate with the time is equal to 0. The change in the concentration of intermediate with the time is equal to 0. So intermediate concentration remains constant. This is constant, and the differentiation of constant is 0. Okay, that is steady state approximation. The steady state approximation is useful to derive rate equation for complex reactions. Okay, for complex reactions, if rate determining step is not known to us, then we can calculate rate equation by using steady state approximation. Generally we proceed with respect to product formation step. We proceed with respect to which step? Product formation step. Right. Next, this is the rate constant K1, and for this rate constant K2, when steady state approximation is valid, and if K1 many times greater than K2, whether steady state approximation is valid or not valid? Not valid. If K2 is many times more compared to K1, in such case steady state approximation is valid. As fast as it forms, it has to be consumed. As fast as it forms, it has to be consumed. Then only its concentration maintained constant and low. Then only its concentration is maintained low and constant. So then only steady state approximation is valid. So in the first case, we will get concentration versus time like this. Concentration of A decreases with the time. Concentration of I, okay, increases and decreases. Concentration of C. Okay, if K1 is many times more compared to K2, concentration of A, I and C we will get like this. Whether concentration of I is maintained constant or not maintained constant? Not maintained constant. So steady state approximation is not applicable. But in the second case, we will get a graph like this. This graph also given once in TSDL. Okay. Concentration of A, concentration of B. Now K2 is many times more greater than K1. As fast as I is formed, it will be consumed. So its concentration may changes like this. Its concentration may changes like this. So almost concentration of I is maintained constant or not? Yes, almost concentration of I is maintained constant. In such case, steady state approximation is applicable. Okay. Only 2 points and steady state approximation. This equation, the change in the concentration of intermediate with time is equal to 0. Next one, when it is applicable. Okay. How to write concentration of intermediate according to steady state approximation? How to write? How to write concentration of intermediate according to steady state approximation? The numerator we have to write where I is forming. In the numerator we have to write where I is forming. What is the rate of formation of I and K1 into concentration of A. In the denominator what we have to write? Where I is consuming. In the second step I is consuming. Other than I we have to write. Other than I we have to write. That is K2 only. So like this we can write concentration of intermediate. So concentration of intermediates we can calculate based on SSA. We can give concentration of intermediates like this only. The rate, okay, in the numerator we have to write the rate equation for formation of I, that is K1 into A. In the denominator we have to write rate equation for consumption of I, other than I we have to write. Okay. Next one, Lindemann's theory of unimolecular reactions. Lindemann's theory of unimolecular reactions. Okay, here activated complex contains only single activated molecule. If activated complex contains only single activated molecule, such reactions are called unimolecular reactions. So what is the mechanism proposed by Lindemann? This is the mechanism proposed by Lindemann. This is the mechanism proposed by Lindemann for unimolecular reactions. Rate constant for forward reaction K1, backward reaction K-1, K2. We generally proceed with respect to which step? Product formation step. This is called what? This A star is called energized molecule. Whether collisions are elastic collisions or inelastic collisions. Inelastic collisions. During collisions between A and A, what happens? Transfer of energy takes place from this A to this A. So this is called energized molecule or vibrationally excited molecule. Its vibrational energy increases. Okay, its vibrational energy increases. This energized molecule or vibrationally excited molecule. Next, what is the forward step? Forward step is called as activation step. Forward step is called what? Activation step or energization step. Backward step is called deactivation step or de-energization step. Forward step is called activation step, backward step is called deactivation step. So they are asking sometimes calculate rate constant for activation step. Calculate rate constant for activation step means what? K1 we have to calculate. Now rate is equal to what? Rate of product formation is equal to what? Rate constant into concentration of reactant, that is K2 into A star. So K2 into, how to write concentration of A star from steady state approximation? We have to write in the numerator where A star is forming. Where A star is forming K1 into A square. In the denominator we have to write where it is consuming. In the backward reaction A star is consuming. So K-1 into A, other than A star we have to write. In this step also A star is consuming, so K2, other than A star we have to write. So this is the rate equation. For the reactions involving gases, we replace concentration of A by pressure. For the reactions involving gases, we replace concentration by pressure. Important Lindemann's theory. Okay, now if you take high concentration or high pressure, what we get? V is high pressure means or high concentration means this is negligible. This is negligible. So AA gets cancelled. So we get K2 K1 by K minus 1. K2 K1 by K minus 1 into A. So that may be written as K infinity into concentration of A. K2 K1 by K minus 1 is considered as K infinity. So it follows which order kinetics and first order kinetics. At high concentration or high pressure it follows first order kinetics. Now at low concentration or low pressure, V is equal to low pressure. This is negligible. Now this is negligible. What we get into K1 K2 by K1 K2 by K2. K2 K2 gets cancelled. K1 into A square. So it follows which order kinetics? Second order kinetics. So mainly you remember these points and what is this? This is energized molecule or vibrationally excited molecule. What is the expression for rate equation? And high pressure it follows which order kinetics? At low pressure it follows which order kinetics? Okay, some additional information also we discussed, that is when it follows first order kinetics and if rate of deactivation step is more or rate of product formation is more. Okay, second order high concentration kadandi. High concentration means this is dominating over K2. K minus 1 into A is more compared to K2. K minus 1 into A is means deactivation step. If rate of deactivation step dominates over rate of product formation, then it follows first order kinetics. If rate of deactivation step is less than rate of product formation, then it follows second order kinetics. If rate of deactivation step, okay, K minus 1 into A dominating over K2 at high concentration, that means deactivation step is dominating over activation step. Okay, next one, if you consider a special case, rate of deactivation step is equal to rate of activation step, and that happens at a concentration of A is equal to A of. If at A is equal to A of, the backward reaction and second reaction takes place at same rate. If you consider, then what we get? What is the expression for A of we got? Once you check, I think K infinity by K1. Antena? The expression for A of is equal to K infinity by K1, or the expression for K1 is equal to K infinity by A of. And one more we discussed, if K dash is first order rate constant at any concentration, if K dash is first order rate constant under any conditions and at any concentration, and either low concentration or high concentration, then what we got? K dash. Okay, first order rate constant means what we get into K dash into A. First order rate constant means we get K dash into A. So this we can write as A into A. So in the place of K dash, what we get? In the place of K dash we will get K2 K1 into A by K minus 1 into A plus K2. If you consider K dash first order rate constant under any conditions, then this is the expression for K dash. So if you plot a graph between K dash versus concentration of reactant, what we get? Hyperbola type of graph we will get. This is nothing but K infinity. That is nothing but K infinity. This is the non-linear relation we have between first order rate constant and concentration of reactant. That is the non-linear relation we have between first order rate constant and concentration of reactant. What is the linear relation we have? If you apply this equation at two different concentrations, before that, if you take linear relationship, and if you take inverse of this equation, what is the linear relation we will get? 1 by K dash is equal to 1 by K dash is equal to what? K minus 1 by K1 K2. K minus 1 by K1 K2 is nothing but what? 1 by K infinity plus K2 K2 cancel. If you take inverse of this equation, 1 by K1 into 1 by concentration of A. This is the linear relationship we will get. This is the linear relationship we will get between first order rate constant and concentration of reactant. That is the linear relation between first order rate constant and concentration of reactant. And if you apply this equation at two different concentrations, we get 1 by K2 dash minus 1 by K1 dash is equal to 1 by K1 into 1 by A2 minus 1 by A1. So if first order rate constant at two different concentrations are known to us, we can calculate what? K1, rate constant for activation step. We can calculate rate constant for activation step. This is the non-linear relation we have. This is the linear relation we have. The same equation we applied at two different concentrations. Okay, from this we can calculate K dash value at two different concentrations. K dash value we can calculate at two different concentrations. That if you substitute here, what we can calculate? K1. What is K1? Rate constant for activation step, forward reaction. Okay, these are some points you have to remember from Lindemann's theory. Okay. Lastly, complex reactions we have. So you may remember some points regarding complex reactions. What are four types of complex reactions we have? One is reversible. Reversible reactions. This is called what? Reversible reaction. So equilibrium constant is nothing but what? Forward rate constant by backward rate constant. Equilibrium constant is nothing but forward rate constant by backward rate constant for reversible reactions. What is the expression for K1 we get? Direct K1 is equal to, I think we got this equation, XE by AT ln A by A minus XE. Antena chudandi. XE by AT ln A by A minus XE. Antena? XE by A minus XE. XE by AT ln XE by A minus XE, where XE is nothing but equilibrium concentration of B. A minus XE is the equilibrium concentration of A. Right, K minus 1. A minus XE by AT ln XE by A minus XE. XE minus X ఇది అంతేగా A minus XE by AT into ln XE by XE minus X. So forward rate constant, backward rate constant, and if you add these two, what we get? K1 plus K minus 1, XE cancel, A also cancel, so we get 1 by T ln XE by XE minus X. If you add these two, you will get equation like this. So ln XE by XE minus X is equal to K1 plus K minus 1 into T. So which is in the form of Y is equal to mx. So if you plot a graph between those two, we will get slope K1 plus K minus 1, intercept 0. Okay, that question given in TSDL. Okay, what is the intercept? Intercept is 0. If have a reaction like this, at a time t its concentration is A minus X and its concentration is X, then how to give net rate of reaction? Net rate of reaction is nothing but what? Rate of forward reaction minus rate of backward reaction, since both are opposing to each other. Okay, reversible reactions are also called as opposing reactions. So what is the net rate? Rate of forward reaction, that is K1 into A minus X, rate of backward reaction K minus 1 into X. Forward reaction rate minus backward reaction rate, K1 into A minus X minus K minus 1 into X. These are some equations you have to remember based on reversible or opposing reactions. This is the expression for forward rate constant, backward rate constant, and if you add these two, you will get like this. Okay. Next, parallel or simultaneous reactions are simultaneous reactions or competitive reactions. Okay, if A simultaneously undergoes two types of reactions, if A simultaneously undergoes two types of reactions to give B and C, rate constant for this K1, rate constant for this K2. Okay, then what is the relative composition of A and B? And K1 by K2. What is the formula for percentage of A? K1 by K1 plus K2 into 100. What is the formula for percentage of B? K2 by K1 plus K2 into 100. What about overall activation energy? K1 EA1 plus K2 EA2 by K1 plus K2. That is the formula for overall activation energy. If EA1 is the activation energy for first step, EA2 is the activation energy for second step, this is the overall activation energy. Simply you remember these expressions for parallel reactions. Relative composition of A and B given as K1 is to K2, percentage yield of A, we can give by using K1 by K1 plus K2 into 100. Parallel reactions. Next we discussed consecutive reactions. Already we discussed consecutive reactions at steady state approximation. Consecutive reactions are nothing but the reactions which takes place one after the other. They are called consecutive reactions. In this you have to remember, okay, here concentration of intermediate or B and changes like this. Concentration of B may changes like this. So at a particular time, that is T max, it reaches maximum concentration, that is called what? B max. At a particular time T max, it reaches maximum concentration, that is B max. What is the expression for T max and B max? Just you remember that. What is the expression for T max? 1 by K2 minus K1 ln K2 by K1. B max expression is A0 into K2 by K1 whole power K2 by K1 minus K2. Okay. The remaining already we discussed at steady state approximation. The same reaction we considered at steady state approximation. Just you remember these two only. What is the expression for T max? What is the expression for B max? What is the expression for maximum concentration of B? And at which time we will get maximum concentration of B. And last one, chain reactions. Chain reactions. Okay, H2Br2 reaction we have in our syllabus. So, write mechanism. What is the mechanism? This is the mechanism. Reverse of second reaction. For example, if you take rate constants K1, K2, K3, K4, K5. ఇక్కడ మనకి ఇండికేషన్ ఇలా ఇచ్చాం కదా K, this is the reverse of second step K minus 2, this is the reverse of first step K minus 1. H2Br2 reaction we have in our syllabus. So this is the mechanism andi. What is the first step andi? Chain initiation step. Here chain initiator is produced, that is bromine radical is produced. And what are these two steps? Chain propagation steps. These two steps takes place repeatedly in cyclic manner. And this is called what? Chain retardation step, chain inhibition step. And this is called what? Chain termination step. This is called chain retardation or inhibition step. And last one, chain termination step. Okay. How to give rate equation? Rate equation we can give by following steady state approximation. According to steady state approximation, we have change in the concentrations of intermediates with time is equal to 0. What are the intermediates we have? One is hydrogen radical and another one is bromine radical. So therefore dH by dt and dBr by dt is equal to 0 according to steady state approximation. That question given previously, okay, both are equal to 0. So by steady state approximation we can get concentrations of hydrogen and bromine. Okay, further we can give the rate equation. So how to get concentration of hydrogen? What is the change in the concentration of hydrogen with time? Where hydrogen is involved? In the second step hydrogen is involved, whether it is forming or consuming. Forming. So which sign we will get? Plus K2 into Br into H2. The third step hydrogen is consuming, so we get minus sign. With which rate it is consuming? K3 into H into Br2. And in the fourth step also hydrogen is consuming, so which rate it is consuming? K minus 2 into HBr into H. Net change is equal to what? 0. Net change is equal to 0. So by using that we can calculate concentration of hydrogen. Second step hydrogen is involved, forming, plus sign. In the third and fourth steps also hydrogen is involved, it is consuming, so we will get minus sign. And if you write for bromine, how we will get? First step forming, so K1 into Br2. Here consuming, so we get minus K2 into Br into H2. Third step forming, so plus K3 into H into Br2. Here also forming, so plus K minus 2 into HBr into H. Fifth step consuming, so K minus 1 into Br power 2. K minus 1 into Br power 2. Net change is equal to 0. Okay, like that we will get a change in the concentration of bromine with time. What is the final rate equation we will get? I think this is one. K2 into K minus 1 by K2. Antena student okkari. K2 into K minus 1 by K1 by K minus 1. Na? Okay. K2 into K1 by K minus 1 all power 1 by 2. Concentration of H2 into Br2 power 1 by 2. So by following steady state approximation, if you do further derivation, this is the final rate equation we will get. So order with respect to H2 is 1, order with respect to Br2 is 1 by 2, overall order of the reaction is 3 by 2. Overall order of the reaction is 3 by 2, or we can write this one like this. K observed into H2 into Br2 power 1 by 2. So what is the observed rate constant? Overall rate constant. K2 into K1 by K minus 1 whole power 1 by 2. So these are some points you have to remember from complex reactions. Okay, just 10 equations you have to remember from complex reactions. So once you revise complex reactions also, in that parallel reactions equations are easy to remember. Okay. Chain reactions also we can remember easily. And only the thing is you have to see from consecutive reactions the expression for T max, B max, and in parallel reactions you have to see the expression for K1, K minus 1. Okay. The further equation you will get easily. If you do K1 plus K minus 1, you will get only 4-5 equations mainly you have to remember from complex reactions. This is observed rate constant. From that, what is the overall activation energy we will get? I gave you shortcut how to write overall activation energy. Activation energy for which step? We have to write second step. Activation energy for second step. Whatever the power we have, power that we have to write at the beginning, power 1 only we have, no need to write. Here we have power 1 by 2 into we have to write activation energy for which step? First step. Activation energy for first step. And if you have in the denominator, we have to give minus sign. In the denominator, we have to give minus sign. What is the power we have? 1 by 2. Activation energy for K minus 1, which step? And fifth step, I think. K minus 1 is fifth step rate constant. So activation energy for fifth step. Like this, we can calculate overall activation energy. Lastly, for example, I am giving like this. For example, this is the observed rate constant. How to give overall activation energy? activation energy for first step, activation energy for first step plus 1 by 2 into activation energy for second step minus, if you have in the denominator you get minus power is 2 activation energy for third step. And like this we can calculate overall activation energy, right? This is the chemical kinetics. You have to revise mainly you revise these points. And almost 90% of chemical kinetics is covered. Okay. First you revise regular notes 3-4 times. First you revise regular notes 3-4 times. After that you follow this short notes. Okay, for doing more number of revisions. And if you are getting any doubt, then you refer regular notes. Okay, right. Thank you. Now take a break.